Hum a single note. Now imagine a friend next to you hums a different note at the same time. What reaches your ear is one single vibration of the air, one wiggling wave of pressure, yet your brain effortlessly hears two separate notes inside it. Today I want to show you the mathematics behind that miracle, how any repeating shape, no matter how jagged, is secretly a sum of smooth, pure waves, and how you and I can extract the exact recipe. Here is exactly what we are going to do together. First, we meet the pure waves, the ingredients. Then we face the real problem, a recipe with infinitely many unknown amounts, and I show you the single trick that isolates any one of them. With that trick, we will derive the famous coefficient formulas from scratch. Use them to demolish two genuine university exam questions line by line, and, at the very end, the recipe of an ordinary parabola will hand us the answer to a puzzle that stumped mathematicians for 90 years. Meet the ingredients. Picture a wave that rises smoothly like a hill, falls through zero into a valley, and comes back up, and then repeats that exact cycle forever. That is a sine wave, and its partner, cosine, is the same shape, just shifted sideways, so it starts on top of the hill instead of at zero. Each ingredient has a frequency. A frequency of 1 means one full hill and valley across our window. Frequency 2 squeezes in 2, frequency 3 squeezes in 3, and so on, wiggling faster and faster. Now the audacious claim, made by Joseph Fourier in 1807, that scandalized the mathematicians of his day. Take any shape that repeats, jagged, curved, even one with sharp corners. Fourier claimed you can always build it from these ingredients: a flat base level, plus some amount of each cosine, plus some amount of each sine, using every frequency. 1, 2, 3, all the way to infinity. Our entire job today is to find those amounts. Stop and feel the size of the problem with me. That recipe has an amount for cosine at every frequency and an amount for sine at every frequency. Infinitely many unknown numbers hiding in one equation. You cannot solve for infinity many unknowns the way you solve ordinary algebra. So how do we grab just one of them, say the amount of cosine at frequency 3, and pull it out of the pile alone? Here is the trick, and it works like tuning an old radio. The air around a radio is filled with every station at once, yet the tuner locks on to one frequency and silences all the rest. Our tuner is this. To find the amount of cosine at frequency 3, multiply the entire mystery shape by cosine of 3x, and then average the result over one full window. I claim that this multiply and average operation makes every single ingredient cancel itself to 0, except the one we are hunting, which survives, carrying its amount. To see why the trick works, we need one small foundation stone, so let us take a 60-second detour and lay it properly. Take any pure wave, say sine, and look at one full cycle. It spends half its time as a hill above the zero line, and half as an equal valley below it. If you add up all the area under the hill and all the area of the valley, they are mirror images with opposite signs, so they cancel perfectly. So here is our stone. The average of any pure wave over a full window is exactly 0. And this stays true at every frequency, because faster waves just cancel in more, smaller pairs. Now watch what happens when we multiply two pure waves of different frequencies, say cosine at frequency 2 times cosine at frequency 3. At each point along the axis, take the height of the first wave times the height of the second and plot that product as a new curve. The product looks messy, but look closely. It is still perfectly balanced around the zero line, hills matched by equal valleys. And you already know what balanced means. It cancels to zero, exactly like our foundation stone. The two waves are, in a precise sense, invisible to each other. That cancellation is not luck, and I want you to see the machinery, not just trust the picture. I am going to hand you two facts from trigonometry: how cosine behaves on a sum of two angles and on a difference of two angles. And you do not need to have met them before. I will put both on screen. They are the only things I ask you to take on trust. And everything we do with them is algebra you can check yourself. Now do something simple. Add the two formulas together. On the right-hand side, the sine terms are identical with opposite signs, so they annihilate. And what remains says exactly this: the product of two cosines equals 1/2 of a cosine at the sum of the frequencies, plus 1/2 of a cosine at the difference. A product of two waves is secretly just two new pure waves added. Now the two pictures snap together. Cosine 2x times cosine 3x is, by our new identity, 1/2 a cosine at frequency 1 plus 1/2 a cosine at frequency 5. Just two pure waves, and every pure wave averages to 0. 0 plus 0. The average of the product of any two waves with different frequencies is always 0. And mathematicians call this property orthogonality. So our radio tuner silences every wrong station. But a tuner that silences everything is useless. So what happens when the dial lands on the right one? Cosine 3x times itself. Picture that product. At every point, the height is a height times itself, a square, and a square is never negative, so the product curve never dips below the zero line at all. There are no valleys left to cancel the hills, and the average must come out positive. Run it through our identity with both frequencies equal, and it tells you the product is 1/2 plus 1/2 a wiggle. So over a window of length 2 pi, the total accumulated area is exactly pi, the sole survivor of the multiply and average trick. We now hold everything needed to crack the infinite recipe, so let us do it slowly and watch the massacre. Take Fourier's full equation. Multiply every term on both sides by cosine of mx, where m is whatever frequency you are hunting, and integrate across the whole window. The flat base term dies because a pure wave averages to 0. Every sine term dies, and every cosine term with a different frequency dies, all by orthogonality. One single term survives, the amount we hunted times pi. Divide both sides by pi, and there it is. The formula that scandalized 1807, derived by you and me from one trick. The amount of any cosine is multiply your shape by that cosine, integrate over the window, divide by pi. Hunt the sines with the same trap using sine of mx, and hunt the base coefficient, a0, by integrating the shape by itself. That is the entire machine, and you now own it. After the break, we point it at two real university exam questions and pull the trigger. Here is the first exam question, word for word, from a second-year university paper. Find the Fourier coefficient a0 of the function 1/4 times, open bracket, pi minus x, close bracket, squared. Before we compute anything, picture what we are being asked. The shape is a parabola, a smooth valley, whose lowest point sits exactly at x equals pi, the middle of our window, rising symmetrically to equal heights at both ends. And a naught is not some abstract token. Divided by 2, it is literally the average height of that valley, the flat water level the shape would settle to if it could slosh level. Now the grind, and I will skip nothing. We take the a naught formula we just built, 1 over pi times the integral from 0 to 2 pi of our function. So the first written line of the solution is simply the formula with our parabola dropped inside it. Everything from here is careful bookkeeping, and we do it together, one line at a time. First move, expand the squared bracket, because we know how to integrate powers of x one at a time, not a bracket squared. Pi minus x all squared is pi squared minus 2 pi x plus x squared. Ordinary algebra you have done 100 times. And that constant 1/4 is just a spectator, so we pull it outside the integral and carry it along. Now integrate the 3 pieces, each with the power rule. Raise the power by 1, divide by the new power. The constant pi squared integrates to pi squared times x. The term 2 pi x integrates to pi times x squared. And x squared integrates to x cubed over 3. Then we evaluate the whole bracket at 2 pi, evaluate it at 0, where every term simply vanishes, and subtract. Combine the 3 numbers. 2 pi cubed minus 4 pi cubed is minus 2 pi cubed, and adding 8 pi cubed over 3 brings us to 2 pi cubed over 3. Multiply by the weighting 1 over 4 pi, and the answer lands a naught equals pi squared over 6. And remember what it means. Half of that, pi squared over 12, is the exact water level of our valley, the average height a listener can now picture as a calm, flat line partway up the parabola. Second exam question. In this one, we will defeat without computing a single integral. Find the coefficient bn, the sign amounts, of the function x squared on the window running from minus pi to pi, symmetric around 0. First, picture x squared, a valley whose lowest point kisses 0 exactly at the center, and whose left half is a perfect mirror image of its right half. A shape with that mirror symmetry across the vertical axis is called an even function, a wave-like sign, whose left half is the right half flipped upside down, is called odd. Now think about what the bn formula asks us to do. Multiply x squared, an even shape, by sine, an odd wave, and total the area across the symmetric window. At any point on the right side, the product has some height. At the mirror point on the left, x squared gives the identical height, while sine gives the same height with its sign flipped, so the product there is the exact negative. Every scrap of area on the right is cancelled by an equal and opposite scrap on the left, and the total is 0 before we lift a pen. So bn equals 0 for every single n, and this is a general law worth keeping. Even shapes contain no sine ingredients, and odd shapes contain no cosine ingredients. Now for the treasure I promised you at the start. Go back to our exam parabola. The valley of 1/4 times, open bracket, pi minus x, close bracket, squared. Its base level we computed ourselves, pi squared over 12. Its cosine amounts turn out to be beautifully simple, 1 over n squared at every frequency n. And I will be honest with you, that computation needs a technique called integration by parts, which we have not built yet. So I will earn it with you, line by line, in the next episode. And today, we borrow the result. and it contains no signs at all, because within its window, the valley is a perfect mirror around its center. Now watch the recipe actually rebuild the shape. Here comes the moment. That equation is true at every point of the window, so let us stand at one specific point. X equals 0, the left edge, where the parabola reaches its full height of pi squared over 4. On the recipe side, every cosine of n times 0 is cosine of 0, which is exactly 1. So each term simply becomes 1 over n squared. The equation now says pi squared over 4 equals pi squared over 12 plus 1 plus a quarter plus a ninth plus a 16th, and so on forever. Move pi squared over 12 across and subtract. The infinite sum of 1 over every square number equals pi squared over 6. Look at it. Add the squares of the counting numbers, flip each one over, sum them all, forever, and out comes pi. Just watch the numbers climb. Sit with what just happened. That sum, 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared forever, is the Basel problem, posed in the 1640s, and for 90 years the finest mathematicians in Europe could not crack it, until Euler did in 1735 and became famous overnight. You just watched it fall out of a routine exam question about a parabola as a side effect of a machine you built yourself in 20 minutes. And notice where pi appeared. In a question about squares of whole numbers, with no circle anywhere in sight. The waves smuggled it in, because every wave secretly carries the circle inside it. Here is what you can now do that you could not do 20 minutes ago. Hand you a repeating shape, and you can hunt any ingredient in its recipe. The base coefficient a0, integrate the shape and divide by pi. Cosine amounts, multiply by that cosine first. Sine amounts, multiply by that sine. And if the shape has mirror symmetry, you can declare half the coefficients 0 without touching a pen. That is exactly what your exam will ask, and more importantly, you now know why every one of those formulas works. And remember where we started. You humming one note, your friend humming another, two notes riding a single vibration of air. Your ear untangles them instantly, because tucked inside your head is a living version of the machine we just built, multiplying and averaging, pulling coefficients out of the air. Next time, we build integration by parts and earn the one result we borrowed today. I will see you there.